Good morning. Today we're going to discuss some numerical problems related to solid state chemistry. Okay. So before going to discuss about the numerical problems, we need to know actually how to solve any numerical problems. Okay. Actually, there are three basic steps by following which we can solve any numerical problems. Okay. The first step is that we have to understand the question properly, and for that we have to read the question. Okay, it may be one time or it may be two time or it may be three times. That means we have to read the question until and unless we understand the question properly. So this is the first conditions, and this is the first step, and this is very important. Okay, you have to read. Okay, and the second um, step is that we have to find out the given data, and we have to note down the given data in our copy. And the third point is, or third step is, that we have to use the given data to solve the questions. And by using the concept of the topics from which actually the question is coming. Okay, by using the concept and by using the data, we have to solve the questions. Understand? So these three are very important steps by using which we can actually solve any numerical problems. So now let us first try to solve the question number 1. Okay, so first what you have to do, you have to read the question properly. Okay, so it is given here that a compound MaXB has CCP, that means cubic close packing arrangement of X. That means X will be what? X will be your anion, because we know that X will going to actually occupy the lattice side, and it will going to form the arrangement, and the vacancies or the vacant site will be occupied by the cations. You have already know these things. Okay, so and here it is also given that the compound is what? MaXB, but we don't know the value of A and B. So what we have to do actually, again here its unit cell structure is as below. That means they also give you the the figure of the unit cells. Okay, and by using this figure or the structure of this one unit cell, we have to find out the value of A and B. If you are able to find out the value of A and B, then you can easily calculate or easily find out the formula of the compound. Understand? Now in the second step, what you have to do, you have to write the given data. Okay, that means here it is given that the compound is MaXB. Okay, now let us concentrate on the given structure, that means the unit cell structure, to find out the actually formula of the unit cell first. Okay, then using that formula of the unit cell, we can calculate or we can find out the formula of the compound, because the formula of the compound is same as the formula of the unit cells. Okay, in case of crystalline solids. So here if you look at this structure, then here you see the square. Okay, the square or the cube represent M. Okay, and the sphere, black sphere, represent the X. Okay, so our aim is what? Our aim is to actually find out the value of A and B. Okay, small a and small b. That means the number of M present in the unit cell and number of X present in the unit cell. Actually, small a represent the number of M present in the unit cell, and small b represent the number of X present in that unit cell. Okay, so let us first try to calculate the number of M present in that unit cells. Okay, here already we know that the M is represented by the square or the cube. Okay, so how many square are present in that unit cell? 1 2 3 4 5. Okay, 5, but one square is present in the body center. Okay, and others are in the edges. Okay, the other four are actually in the edges. Total 5 squares are present. Okay, so again we know that in case of if the constituent particle or if the particles is present in that body center, then it will contribute 1. Okay, understand? We already discussed this. Okay, if it is inside the body center of that unit cell, then it will contribute 1, because the whole whole particle will be present inside that unit cells. Okay, now let us calculate the contribution of the remaining 4. Okay, so all the 4 stars actually contribute equally to to the actually to the to the unit cells. Okay, so by calculating only one we can have the other values. Okay, so first concentrate only one of this among these four. Okay, so let us suppose this one. Okay, so here if you look at this particle, okay, which is represented by this square, actually this will be this will be inside total 1 2 3 4 4 unit cells. That means this M, okay, which is present in the edge of that unit cell will be actually inside 4 unit cells. That means we have to divide this this unit cell or this constituent particle by 4 to get the contributions. Okay, so how many total, how many 1 2 3 4 4 constituent particles are present? That means 4 constituents particle which is M are present in that edges. So we have to write 4 by 4, that means 1. Understand? That means total number of A will be what? 1 plus 4 by 4 is equal to 2. That means total 2 number of M are present inside that unit cells. So A is done. Okay, so now concentrate on the B. That means now let us find out the value of small b. Okay, so to calculate the value of b we have to find out where actually the x are present. Okay, so here actually the x are present in the corners, all the corners of the unit cell, and all the 6 faces, actually face center of the unit cell. Okay, so first concentrate on the corner particles. Okay, so here the particles are represented by what? The black sphere. Okay, so here total 8 1 2 3 4 5 6 7 8 corner particles are present. Again we know that the contribution of the corner particles are 1 by 8. So total 8 actually x are present. So 8 into 1 by 8, that means 1 contribution will be come from the all the 8 corner particles. Okay, and the face centered that means the face center, for the face center particles total 6 face centered particles are present, and we already know that only half contribution will be come from the face center particles. Okay, so here 6 into 1 by half, that means 3. So total how many? 1 plus 3, total 4 x will be present inside that unit cell. That means the number of b will be what? 4. So then that means we have now the value of a which is 2 and the number of b which is 4. Hence our formula of this compound will be what? M2x4, or we can actually simplify this one, and if you simplify the formula then it will be what? Mx2. That means the option A will be your correct options. Understand? So this one is done. So now let us try to solve the question number 2. Again in this case also we have to read the question properly first. So here it is given that the arrangement of X negative ions around A positive ion in the solid AX is shown in the figure below. Okay, and here the radius of X negative is given and we have to find out the radius of A positive ion. So if you look at this figure then you see the first layer is composed of 3 constituent particles and they will going to create a triangular void. Okay, and above that first layer the second layer is there, but here the triangular void which is created by the second layer, the apex of the first layer is opposite to the apex of the second layer of the triangular void. That means the void which is due to this packing will be actually your octahedral voids. Okay, so always remember that if the void is octahedral, okay, then the radius ratio, that means the ratio of the radius of the cation and anion, okay, is actually between 0.414 to 0.732. and if it is not given or not mentioned in the question that the types of actually radius ratio, then you have to use the that limit, the which is actually 0.414. okay, and we already know that the octahedral void is actually occupied by the cation. Okay, and the constituent particles or the actually lattice site will be occupied by the anions. Okay, so here actually it is shown in this figure also, the octahedral void is occupied by the cation which is A positive ion. Okay, and if the cation is totally fit properly fit in that octahedral void, then also the radius ratio of that that means the radius of the cation divided by radius of the anion, which is R positive by R negative, will be 0.414. okay. But if there will be some mismatch, that means if the size of the cation is slightly higher or larger than the size of the octahedral void, or if the size of the cation is slightly smaller than the octahedral void, then there will be some defined value. That means we have to use the value in between the 0.414 to 0.732. okay. And also if no information is given in that question, then also we have to use the radius ratio as 0.414. okay. So for this equation we have to use the radius ratio as 0.414. so we can write radius r, actually r a positive divided by r x negative is equal to 0.414, and we have the value of radius x negative, which is 100 picometer. So we can put this value inside in that equation, and by using just simple cross multiplication we get the value of r a positive. okay, that means the radius of the a positive ion, which is equal to 0.414 into 100 picometer. That means 41.4 picometer. So that means the option C will be your correct option. Understand? Now let us discuss about the question number 3. okay. So here it is given that a crystalline solid of a pure substance has FCC arrangement with unit cell age of 400 picometer. That means the arrangement will be what? FCC. okay. And the cell age is 400 picometer. That means the value of A is 400 picometer, and the density is also given. It is as 8 gram per centimeter cube. Then here what we have to find out, we have to find out the value of N if the number of atoms present in 250 gram of the crystal is N into 10 to the power 24. okay. First of all we have to write a given data. okay. So here first of all it is given that the arrangement is FCC arrangement. That means the number of atoms present inside that unit cell will be 4. That means Z will be 4. okay. And the cell age is equal to 400 picometer. okay. So we can write it 400 picometer, and even we can convert it in one unit system, maybe SI unit or maybe CGS unit. So we can convert them in CGS unit. okay. So it will be your 4 into 10 to the power minus 8 centimeter. okay. Then the density is given as 8 gram per centimeter cube. It is already in CGS unit, so no need of converting it other units. okay. So then what we have to do, actually the number of atoms present, and also the the weight of the crystal is given, which is W. okay. W, weight of the crystal, is equal to 250 gram. okay. And now what we have to do, we have to find out the value of capital N if the atoms present in that 250 gram of crystal is N into 10 to the power 24. So now actually we can use the formula of the density, which is Z into M divided by Na into A cube. okay. This is already discussed in the previous classes. okay. So we can use this formula to solve this this problem. okay. Again we know that the number of atoms is equal to weight of the crystal divided by atomic mass into Na. okay. Na is what? Na is actually Avogadro number, and here actually capital M will be your atomic mass. okay. So once we have the value of capital M, then we can find out the value of number of atoms. okay. So by using the number of atoms we can calculate the value of capital M. So our first target to find out the value of capital M by using the formula. okay. So the capital M is equal to small d, which is density, into Na. Na is Avogadro number, into A cube, which is actually the edge length cube, divided by Z. Z is what? The number of atoms present in that unit cell. okay. So it will be equal to, so what we have to do, we have to just put the values of the respective actually we have to put the respective value in that equation to find out the capital M. okay. So if you put the value D as 8 gram per centimeter cube, and Na is equal to actually 6 into 10 by 23. Actually it is 6.0 into 10 by 23, but instead of 6.0 into 10 by 20 we can even use 6 into 10 by 23 for simplification. Okay, into a cube, the value of a is what, 4 into 10 to the power minus 8 centimeter. So we have to cube this one and divide it by z value is what, 4. Okay, now we can put a value of m in the equation, which is actually number of atoms is equal to weight of the crystal in gram divided by m, okay, into Na. So by putting this value of m here, then what we have, the value of the number of atoms as 2 into 10 to the power 24. Okay, so and in this question it is given that the atom number of atoms is capital N into 10 to the power 24. That means the value of n will be what? Value of capital N will be your 2. That means the option C will be the correct option. In the next question, which is question 4, we have to find out the packing efficiency of two-dimensional square unit cell. Okay, so that means this is 2-dimensional, okay, not 3 dimensions. So we know that in case of 3-dimensional structure, the packing efficiency is equal to the total volume occupied by the spheres present inside that unit cell divided by total volume, okay, of that unit cell into 100. But here the structure is what, 2-dimensional, so the packing efficiency equation will be different. Okay, and the packing efficiency for 2-dimensional unit cell will be the total area of the spheres present inside that 2-dimensional unit cell divided by total area of the 2-dimensional unit cell, because this is 2-dimensional, so only area will be possible, okay, not volume. We cannot get volume of 2-dimensional thing, and we have to multiply by 100 to get the efficiency in terms of percentage. Okay, so by using this equation we can solve this problem. Okay, so now coming to the problems, here actually the structure of the square unit cell is given. So let's suppose the radius of the the constituent particle is small r, then the diagonal will be what? The diagonal of this square unit cell will be small r plus twice r plus small r. That means it will be your 4r. Okay, again let's suppose the the length of the edges of the square unit cell is capital L, then also the diagonal will be your root over capital L square plus capital L square is equal to root over 2 capital L by using the Pythagoras theorem. Okay, so the 4r is equal to actually root over 2l, or capital L is equal to 4r by root over 2. Okay, so what would be the total area of this square unit cell? The total area of the unit cell will be L square. So L square, or you can actually express this L square in terms of small r also, then it will be your 4r by root over 2 whole square, okay, is equal to actually 8r square. Okay, so now we have the value of total area of that square unit cells. Now let us find out the total area of the spheres which are inside that unit cell. Okay, so for that we have to find out the number of sphere inside that square unit cell. Okay, so one atom is present in that center of the the unit cell, so one contribution will come from that. And what about the other 4 which are actually present in the corner of the unit cell? So if you look at only one atom which is present in that corner, then actually it is shared between total 4 4 unit cells. So that means we have to divide by 4 to get the contribution of the sphere which is inside that unit cell. Okay, so total we have 4 corner atoms, so we have to actually multiply the 4 into 1 by 4. Okay, so that means that first this 1 is actually coming from the contribution of the center atoms, then this 4 into 1 by 4 is coming from the contribution of the 4 corner atoms. Okay, so that means we have total 2 atoms present inside that square unit cells. So we have to find out the area of the 2 atoms. Okay, to find to actually it is actually equal to the total area of the spheres which is inside that unit cell. Okay, so the area of each sphere will be what? Pi r square. So total area of the spheres will be 2 into pi r square. Okay. So now we have the value of total area of the square unit cell as well as the total area of the spheres which are inside that unit cell. So we have to just put this value in that equation, and by using this equation and the data or the value of this, that we have the value of the packing fractions, which is equal to actually 78.5%. Okay, so the option A will be the correct option. Now coming to the question 5, which is actually a simple objective type question. So here what we have to do, we have to find out the correct statements for cubic closed packing 3D structure. Okay, so coming to the first point, which is A, the efficiency of atom packing is 74%. This is correct, and you can go through the calculation of packing efficiency for CCP unit cell to find this one. Okay, and the second point is that number of tetrahedral and octahedral voids per atoms, not per unit cell. Okay, per atoms. So this is slightly a tricky one. Okay, per atoms and are what? 2 and 1 respectively. Yes, this is correct, because we already know that for CCP or HCP unit cell, we know that the octahedral void, if the number of atoms is capital N, then the number of octahedral void is also capital N, and if the number of atoms is capital N, then the number of tetrahedral void is what? 2n. So it is correct. Okay, so that means if the number of atom is 1, okay, then the tetrahedral void is 2, and if the number of atom is 1, then octahedral void is 1. So this point B is also correct. So that's why I actually told you to read the question properly. Okay, because sometime it will, the question will be molded form. Okay, some tricky questions may come. Okay, so you have to read the question properly. And the third option is the unit cell edge length is 2 root over 2 times of that radius of the atoms. So this is also right. So you can find this option in the calculation of the packing efficiency part. So that means option A, B and C all are correct. So option D, which is all are correct, is the correct option. Understand? So option D is correct. Hope you understand the numerical problem and solution, and also the objective type questions, and try to do numerical problems as many as you can. Okay, because if you do many numerical problems related to one topic, then your concept will be clear. Okay, thank you.